7 leads off with getting a little more particular about defining quantitative data. Remember, quantitative data was numbers. Okay, we're taking a look at numbers. What we're asking for, we get numbers out of. And it defines this term called a random variable. Now, I hate the definition in the book. If you look on page 391, take a look at it real quick. Let me say the definitions to say a random variable is a variable. So they're using the definition of the word in the definition. But the bottom line is that variables you've dealt with before. Way back in Algebra 1, you said let x equal something. And some sort of a number you were trying to solve for. A random variable in statistics always takes on a numerical value. So let's talk about this thing called a discrete random variable. Okay, let me give you an example of what I'm talking about. So let's say we flip a coin 3 times. We've done this any number of times. So I'll write down all the possibilities. What heads, 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 tails, heads, tails, heads, heads, tails, tails, tails. There's 8 of them. Okay, so there's 8 different things. And I don't know if it was someone in this class or another class said, well, why don't we just put that here as our sample space? That's all the different things that can happen. And you might do that in some situations. But what a random variable is you have to take these members of the sample space and ask some kind of question that's going to give you a number. For example, the one we've done a lot of is how many heads am I going to get? So in this particular case, I could get 3, or I could get 2, or I could get 2, and so on. This is an example of a random variable for this sample space. So we say something like x is the number of heads, or h, and that represents a random variable. Now, what makes it a discrete random variable is if all the possible things that could happen, if there aren't that many of them. So if I flip a coin 3 times, what are all the possible answers I could get here? I might have 0 heads, I might have 1, 2, or 3. That's it. There's only 4 options. Okay, so that's what we define as a discrete random variable. When I have a countable number of possible numerical, okay, not letters, numerical outcomes. And we've done this before. The probability of not getting any heads, so it says it's 1 out of 8. So the probability model for this looks like this. They all add up to 1, and we have the probability model. Right here, I like you guys to write the number of heads. And this is the probability of the number of heads. Write the value of that random variable right in there. But when you hear the word random variable, just remember it has to give us a numerical answer. All right, something very important to remember when we're dealing with a discrete random variable. Let me ask you this question. Would these give us the same answers? The probability that we get more than 2 heads and the probability we get greater than or equal to 2 heads, would those give us the same exact answer in the discrete random variable? No way, right? Probability of more than 2 heads, that's just this guy, 1/8. Probability of 2 or more heads, it could be this guy or this guy. We'd add those up and it would be 1/2. So be very careful. These 2 symbols mean something very different when you're dealing with a countable number of outcomes. That's one type of data that we work with, quantitative data. This is the other type of quantitative data that we work with, and it's called a continuous random variable. What's the difference? Well, there's just a ton of outcomes. I couldn't even list them all. Classic example of a continuous random variable. How much a baby weighs when it's born. You might be saying, well, wait a minute, that's countable. I was 8 pounds 2 ounces. I was 7 pounds 3 ounces. There's only so many of those it could be. Well, no, let's think about this really. Maybe you were 8 pounds 8.2, 6.4, 9.3, 7.2, 9.9, 6. Depends on how good that scale is, right? To get the exact weight. So there's just an infinite number of weights out there. Okay, that's considered a continuous random variable. There's no way I can just write them all down here real easy. These two you did for your warm-up are two examples of continuous random variables. These density curve. Now, density curve. Skylar, what was the big hint I was giving you when I said that both of these, both a uniform distribution and a normal distribution, are density curves? The big hint was?
They both have an area of 1.
Yeah, they both have an area of 1, okay, underneath their curve. So if they both have an area of 1, let's look at the uniform distribution now. If it has an area of 1, how tall must this thing be?
1/4.
Yeah, 1/4. 4.25, many of you said. This is a rectangle, right? So 4 times 1/4, that gives us our area of 1. All right, so how'd you shade the first one?
This one I counted off 0 to 1, 2, 3, 4.
Okay, 2, 3, 4. Okay.
And shaded between 1 and 3.
So you put your things up here, 1 and 3, you shade it.
Yeah.
Now second one here, let's just shade the next one. So I've got 0 to 4, and I'm doing greater than 3.5, so if I got my 1, 2, 3, so here's my 3.5. How'd you shade this one?
Will technically be like a dotted line, because it's...
Technically it would be a dotted line, but we're going to get away from that actually today. We're actually going to get away from a dotted line and a line. So go ahead.
So the line and then to the right.
So we shade to the right. Did we ever draw dotted lines in these normal curves when it was greater than or equal to? No, we never drew dotted lines. We don't have to worry about that. So I guess my question is, you were kind of alluding to it. Is there any difference between a less than or equal to or a less than sign in terms of how we go calculate these areas? And the answer is no. And here's the reason why. And what if I'd have asked you the question on this uniform distribution, what's the probability that it's equal to 2? I got this curve here. There's my 0, 1, 2, 3, 4. And I'm going to do my area and then shade it, so I draw this thing up at 2, but is there any shading to do? What's the area of the thing I just drew right there? 0. There's length times width, right? There's nothing to multiply here. Back in geometry days, if you remember, a straight line doesn't have any length or width. It doesn't have any width. So there's no area at any one particular spot. Let me say it another way. Let's go back to that baby weight. Okay? So you were 6 pounds 8 ounces at birth. Okay? So if I said, hey, what's the probability of being exactly 6.8 ounces at birth? There is no chance for that. You were probably 6.80000006437. The probability at any one spot is impossible. Okay, and you see that when we draw these pictures. There's nothing to shade. There's no area in between them. Okay, so we'll get back to this in a second when we're dealing with this. But bottom line is, I don't care which way you write it, it's not going to change how we figure out these probabilities. All right, let's go figure this out again. So what did you figure out as probability, or how'd you do that?
50%. It's if each number is a quarter.
Okay, so that's one way to look at it, right? He broke them into quarters. And these were 2 of the quarters. 2 over 4 is 1/2, which is 50%. What's another way to do that? It's a rectangle, so.
So you just do the length of the shape.
And what's the length?
2.
2, and what's the height?
1/4.
1/4. 2 times 1/4, 2 over 4, 0.5, you get the same answer. Okay. Right, Karen? So how about this one here? How'd you figure this one out?
I did the same thing. I broke it up into quarters, and then I did it the 1 into an 8.
So this is it's 1/8, but now doing it another way with the rectangles.
You could do an 8 times a quarter to the 16, which is
What is the length there?
0.5.
5 times 1/4, and you still get your 1/8, which is your 0.125. So either way, create rectangles, do length times width, or if you can break them up into sections, you can figure out the probability that way. All right, now let's go on to the normal distributions. James. How did we, no, not that James, you James. How did we draw this picture? I hope the first thing you did, remember, as soon as you see that word, we draw our normal distribution. Go on. Now what do I do? You have a million of these pictures in your notes.
Well, I drew a line. Right. Oh, I'm sorry. Okay. You put 70.
Good, yeah, we have to identify the mean. That's the first thing we put on there. Good.
Then you draw a line dividing both sides. And then I shade it first before I put the number there.
Okay, let's put the number there first.
And this is where things get complicated.
Yeah, we haven't done anything yet.
Yeah.
Go on.
Yeah, no.
We're doing this problem right here. What do I do?
72 minus 70 over.
Oh, before the 70. I'm putting stuff on my picture.
You actually write 72 on the graph? Oh, okay. Well, then do that.
Reese!
You do the mean plus.
Not yet, not yet. I do my picture first. I want to shade my picture first.
So it's on the right side.
Come on, guys! Killing me!
Why do you have to write it down?
Mason.
You put 72 down.
Okay, yeah, that's the one. Now, the last two classes, I've had all kinds of people saying, oh, I got to put 76 and what. No! I just put the stuff in the problem that I need to solve this particular one. So correct 72, I draw my line. Okay, it says greater than 72, but I just draw it right at 72. I don't make it a little bit greater than 72. I don't draw a dotted line. Okay, we go right from there. Continue.
You shade to the right.
Correct. So that's what I'm looking for. Next step.
You find your z-score.
So before that, I write
The z-score. The standard deviation.
formula. I always write down the formula.
Z equals x minus mean divided by standard deviation.
And remember, z-score is how many standard deviations you are from the mean. So how many standard deviations is 72 from 70? We plug in the numbers. 72 minus 70 over 6. So what's our z-score?
It's 0.33.
0.33. It kind of keeps going. So now what do I
Go to
do?
your chart.
No.
You label that.
Yes.
Under.
Right underneath here, you put the 0.33. Anything else?
Then the other standard deviation, like the actual standard deviation.
No. Reese, you want back in the party?
0.
Yeah, we're going to put 0 here. Remember, this second row of numbers, that's how many z-scores. That's called the standard normal curve, where the mean is 0 and the standard deviation is 1. We always fully identify that. Now we can go to our tables. What do we do?
You go to your table and you go to 0.33.
We go 0.33 is a z-score, and what does it tell you?
It's 0.62.
So that's the answer, right?
Yeah. No, that's not the answer.
No.
That's the other side.
Yes. Remember, when you look it up in the table, look on the top of that chart. It's showing you what that probability represents. So this is 0.6, whatever you said. Then what do?
You subtract that from 1.
So 1 minus the 0.6 what?
6296.
So that ended up being 0.3 something. Okay, so that's the answer you write. There's a 30 whatever percent chance of getting I don't know, is this baby weight? I hope that's in ounces. Baby weight of more than 72 ounces. Even that's not very good. That's like a 4-pound baby. Okay, same idea with B now. Your picture should have the mean. Here's 75. Here's 62. The shading would be between it. Go find your z-scores. Write the z-score formula. Plug them in. I think this guy is negative what?
1.3.
1.33. This guy is like 0.833. Now, what do I use on my tables?
You go to the other chart. Well, no, on the table you basically do the same thing
Okay.
that you did on the
Okay.
and you get like 0.0918.
So that's for this one?
No, that's for the 60.
Take me through the steps. I go to my charts, I look up 0.833.
Right. And then you get 0.7967.
Okay, so that's 0.7967 is all the way over. Go on.
And then the other one's 0.0918.
And then what do you do with those two numbers?
You
Subtract them to find the probability that's in the middle. Okay? These are both examples. Anytime you do a uniform distribution, anytime you do a normal distribution, those are both examples of continuous distribution charts. So, if I was to fill out a continuous distribution chart, we need to use intervals. Because I just can't put the probability of 1 and 2 and 3 and 4. Those are all going to be 0. So an example on the uniform distribution, I might go anywhere from 0 to 1, 1 to 2, 2 to 3, 3 to 4. These would all be 25%. That's what we expect out of a uniform distribution, right? The probabilities would all be the same straight across. If I was doing a probability model for a normal distribution, I don't know, I might break it up as, I don't know, less than 50, 50 to 60, 60 to less than 70, 70 to less than 80, and then greater than 80. I could go do this work for all those intervals. If I added them up, they'd all be equal to 1. Yeah.
So, if they're the same thing, then don't we have repeats?
Then we have repeats. I thought you were asking
Well,
a question.
50 to less than 60. 60 is in 2 columns.
Okay, so he says we're going to have repeats. In fact, I don't even need this. So now I really got your repeat going on, don't I? He says, hey, wait, we got repeats, don't we? On those sides. Well, what's the probability at 70? What? 0. So the probability at any one spot is 0. So if that's the case, we don't have a repeat there.
Oh.
Okay. In terms of if I was going to use this probability model to do it. Okay. I see what you're saying. Where would a score of 60 go? That's why I did include these. Less than 50 and then 50 to. Okay. So I still would include those, but understand at any particular spot the probability is 0. So. Okay, all right, so big deal today. 2 different types of quantitative data. One of them is discrete, where I can get a countable number of numerical outcomes. That's a random variable. Or it's continuous. I got so many outcomes, I have to represent them by an interval. Just remember that that symbol means something in a discrete. That symbol does not mean anything. It means really the same thing when we're talking about continuous data, because the probability at any one spot is nothing. Questions, comments?